Hello everyone. So let's see where we left off yesterday. Yesterday, I guess we were trying to fix a bug regarding malloc because my kmalloc was not working for some reason, and I was just hypothesizing with some ideas of what could be going wrong by the end of the stream yesterday. And we also wanted to fix one of the label that which is hard coded and which was causing an issue because as the size of the kernel ELF grows, it's sort of overwriting this address and it's moving around. So it was we'll have to fix this part and then overall test the switch between multiple processes because we already added the syscall that can call the block layer and do the write operation, and it needs to be called from two different processes to test if the actual switching and the parallel syncing works. That was the whole point. So we'll do that today, and yeah, overall we've been trying to write our own kernel, and we have the initial MMU unit and a little bit of scheduling and a little bit of block layer, and also virtual separation is working currently. Yeah, overall everything seems to be working, so we'll get into the bugs that we wanted to fix yesterday. Let's start with this comment where first here I'm just trying to this is my vector table, and my vector table needs to be the beginning of the vector table needs to be put into this vbar el1, so that whenever there's an exception happening, my exception handler will know which handler to call. So if this table is not in the right location, whenever we get an exception, things might go wrong. This is what was one of the issue that was happening yesterday. And whenever I try to build, whenever I try to run, sometimes it was working and sometimes it was not working, and the case was because in certain runs we were overwriting this address. So today let's start by making it dynamic so we don't have to worry about this issue at all in future. And the key for that is to load labels address into register in OM, because what's happening here is that we have this vector dot s, it's just pure assembly, and it has one flag, one label called vectors, and this is the address we want, and this address can be anything, but we need to currently we are hard coding it, and we know that the vectors will be put into this address. That's why we are able to calculate it, but then it is causing issues because as the file size grows, things are moved around and it's fucking with us. So it's better to just directly use the label and get the address instead of just putting the address there. And looks like all we have to do is that ldr and equal to label, and I think we tried it and it did not work for some reason. Yeah, what the fuck is happening? Even here we are updating, and then again we do that here. Oh, okay. After, so initially we were able to update it, but after we start the MMU unit, we need to somehow change it into our virtual space. Okay, so that was the actual issue. Okay. So because as soon as we enable the MMU, this whatever address may not be in my kernel's page table. So that is why I have hard coded it with by adding FFF in front, and I have added a comment saying that convert this into this. Okay, makes sense. So even for this we still can do the same thing. Take a read address. Read the address of the label and FFF the upper bits upper 64. We just want to convert the upper bits into FFF. I don't know. Isn't there anything simple, easy syntax? So to load a label, what we have to do is use this. Okay, so if it's a 64-bit address, we do have to use this version. We can't simply use LDR. But then how come this works? I think we can just simply use the LDR. What is the LDR? LDR is just, I guess, oh, okay, it loads a 34-bit address. Then how come this was working? So it was fluke. That's sad. I guess we have to do this because we have to use load operation to take the entire thing. Okay, then let's try it. So we take the entire thing, which is vectors. This is the label that we want. Now we load it into x0, so we'll use adrp. Then even this instruction should be wrong, right? Because If LDR is just going to take the 34 bits, 32 bits, it's going to take this and it's gonna take this. And what the fuck am I even doing the for? It's just so fucking shitty codes. Mm. Is it 32 bit or 64 bits? Bit or 64 bit. So it is possible to. Is it just fucking with me? I don't wanna use this. Find a good solution. I need to confirm if someone else can say the same thing. Okay, this one looks better. Let's see. Mm. Okay. So as per this blog, looks like LDR operation is supposed to only do linker time relative operation. So this is almost handled by only if the linker knows it has a specific address for a label, you'll be able to put it here. But if we use ADR operation, it's almost like runtime, because assembler just generates a relative operation to the PC. So that way, as long as the as long as the label is either above or below the current PC, we should be able to index it. And that's why labels used by ADR must be within the same code section. Yeah, the address instruction is helpful for calculating the address labels at runtime, because the address can't be determined at the compile time. This is the difference. So if we want LDR, if we know the address during either the linking process, we can use LDR. But if we can only know the address during the runtime, we should use ADR. Okay, I did not know this. Okay, but I think LDR can address 64 bits, so that's why our operation was working. So the operation is correct, and in this case we are just loading hard-coded addresses here, so it is perfectly fine. But in this case we cannot use LDR because the vectors does not have a address yet. There's no way to tell where the vectors will be present within the binary ELF. That's why probably this operation did not work for me. Or maybe in my case it is possible to get the address, and I have only tried this to get around the MMU units. I'm a bit confused. I guess in my case it's just that after I enable the MMU unit, the VBAR value needs to be FFF, and that's why I'm trying to do it again. So if that's the case, then I think I can just use this, and then what I do is I'll put an operation like this. So in x1 I'm just gonna put FFF and make everything as just zeros, and I'm gonna AND them, because no, I'm gonna OR them. That way I'll just get both sides. Storing the register in the destination R1 R2. Okay, ORR destination R1 R2. Okay, I think it should work. Let's try. If we build it, looks like it worked, because we have syscall write is called, and then we have the write, and then finally we have the second issue that we found, which is the malloc is not working for some reason. So that's the second issue we found, but this was the first issue. So to confirm things, let's just build it and break near kmain. And we can just break here. What is the last C? And we can put FFF. And now if we run it, we are here. At this point we can check the vbar value. We can say info vbar el1. Okay, we'll just put vbar. What the fuck? Info registers. Oh guys, you have to put info registers. Okay, and as you can see, now the value is in 802800, and we have the upper bits as FFFF. So that's good. So we don't have to. So here we are just converting the physical address into virtual address by adding FFF in upper bits. We are not doing this. That's not an issue because we are loading the vectors and it is fine, working just fine. So what we actually do is just because we have enabled the MMU here, we have enabled the MMU here. Because we have enabled the MMU here, we have to convert the physical address into virtual address. Nothing much. It's all good. Okay, now we're done with the first issue. Now we have the second issue, which was pretty different that we tried yesterday. Where is it? We go into our MMU, and this is where the issue arises. So let's run it and see. Looks like something else is happening. Okay, so it just took some extra time. Okay, but whatever. So, but we are here. We have this. We did make the proper syscall from the user space, and we got our syscall handler was able to catch that, and we have the initial print message with saying the syscall number, and so the syscall write is called, and then we have the starting to write message, and then we have called the actual block read. Within that we have multiple malloc operations, and one of the malloc operation, the first one, we were inside it, and the virtual address, we want to convert this virtual address into physical address with we want to map this virtual address to this physical address in that table, and the total pages we want is just 1, so we are using the index 0, and when we do that, when we finally do that operation around here, Maybe we are faulting even before that. We have to count all the prints. So we have this message here, and just after that we are supposed to get index equal to 0. Okay, the message is here, so it's just there's a line break missing. Maybe we'll put that line break so it will be a bit easier to read, and we don't have to put that into our memory. Okay, run it, and it is taking some time to write, and it says it did not find anything. So should we wait this time? Because it says no device found. Maybe it's because where do we see if a device is there or not? No, it is working. Because currently we just move past that, and we were able to do the block read, and yeah, it's just taking time because we have enabled the logs, and every operation is just too slow because Chemo has to log every damn thing. Okay, finally we are here within this map pageable entry, and we have the first message, which is this line, and then we have the second print statement, which is here, which is just printing the current index, current VA, and the L2 index, and L2 table address, and L3 table address. And the next operation after that is we set L2 table dot index equal to descriptor. It's L2 table. Okay, it's L2 table dot. Okay, so what's the L2 table index value? This. Let's copy that, and if we go here, paste it, and we were trying to access this memory, and what did we get? Let's just put Camo. We were not able to write to this address, C001700. Why? Is there any relevance, like maybe we don't have enough space or anything like that? Let me double check. Let's just double check our code. But as per the logs, it says we have a, maybe we are interpreting it wrongly. Let's check it. Maybe it's a different fault. Yeah, yesterday we checked, the fault was actually permission error. So let's just confirm that. So this is the code. So it's like 960045. So that means This is the virtual address that is failing. Non-existent or unmapped physical address. So this is what we want to disassemble. So what is that? We need to stop around kmain, run it, and then let's examine this. It's something random, so maybe we need to be a bit more. Let's put 50x and put 50 instructions. 50. Disassemble match page table entry. And our address was 1184. And if we go back here, it should have been inlined. Okay, still let's try if there is anything called table. Disassemble set table entry. So it is there. And does the address match? Yes, it matches, and we fail at this location. So it's good. Let's see. Let's stop here then. If we break here, we'll have to go through it multiple times. So we better build it and break at sys right. Run it. Okay, here we are. Now we can again break in this location. Wait, disassemble set, and I still don't understand why it's not inlined. It must be inlined. Should have been inlined because we have specifically mentioned that inline everything, but for some reason it did not do that. Okay, that's for another day's debugging, and it's not here either. Possibly because we have to get into the interrupt only, then this page tables will come back. Okay, so we'll continue until what? Yeah, we can just simply put the breakpoint here. And maybe also put a breakpoint and run it. Okay, so now we are here. And probably that's the epilogue. And probably this is the info registers. We want registers x8, x9 and x10. So we want to it calculates the target memory by taking the value in the base register. We have all the base registers, so it's x8, x9, x10, right? I can give that information too. So we have x8 with some readable value, x9 which is also readable value to be stored, because as we can see we want to store an address, and this is the base address which is the table's address, and offset is 0 which is index. Okay, what contains this? The targeted address is calculated as equal to fault address register shows the address occurred at something. Okay, this indicates ESR value, synchronous external abort and write operation. CPU successfully translated the virtual address, but the external memory system are attempting to write to the physical address. So you mean this is mapped to some random address? Okay, what context are we currently in? If we are at this point, that means we are inside. Let's do some testing. Is this accessible? Oh, it's not accessible. But if we do 2, 3, 4, even this is not accessible. So breakpoints at that very instruction shows So I think the issue is that I am coming from EL1 to EL. The context is that I am inside a syscall exception. So I am coming from EL0 into EL1. Because within EL1 there was no issue with this address 0x7000 because that has been accessed previously. The question is, when we switch from EL1, EL0 to EL1, shouldn't the tables be switched automatically? I mean, it should have switched. So when I'm back into EL1, do I have to switch anything back? So yeah, I don't need to manually switch anything. No, not from EL1 to EL0. I mean from EL0 to EL1 during the syscall interrupts. And the exception detects the SVC instruction and it uses the to correct handler, and so far everything is good, and saves the current state and reads the determine the cause. So when I'm within the kernel context, I think I should have this page table entries. Uh, let's try one more time. Mm, we are inside EL1, but we don't have the table entry for this at this point. How is that possible? Shouldn't we be? Hmm, I don't know. Hmm. Half shit. What I'm trying to understand here is that if I am actually in the EL1 context, then the page table entry should have a value for 87, this address that we are trying to fetch. Because even before getting into the tasks, we have created this, and the L2 index is this 54. and it's this. Wait, I'm confused. Wait. We put this right first. Go into this right. Go into this right. And then we can break right before the set table entry operation. Oh fuck. I pressed continue 2 times, so it fucked up. Okay, we'll do the same thing again. Okay, now we are inside this right, and now we break into this address. It's also put FFF once more. Continue. Now we are here. And the address is this. L2 index is this. Which is C7 something. Right. But okay, maybe we are no. It is fucked here, so we are only passing 3 values, and one is current L2. Okay, we don't print current L2 anywhere. And current L2 is this. This is what we will use inside kmalloc. And kmalloc needs L2 table. Okay, it's fine. And that address is not reachable in this at this point of time. If we try to allocate more than 10 L3 tables, we'll get an error. And our L2 index is just L2 index is just 0. For every L2 index, I need to create a L3 table, okay? And we use this logic to create the table. Okay, that is also fine, but we don't even use L3 table right now. Currently within L2 table we are getting the error, and this is the L2 table's address. And the error is this is not accessible. So it's as simple as that. I just need to figure out why in this current context my table does not have this entry. And what is my table? Info registers. And it's TLB. Is it TBR0EL1? I guess it's TBR1EL1. And the address is that. This is our page table. So it is pointing to the correct table. Which is this, which is our L0 base. The question is it actually using this or is it using this? If it uses this, then there won't be anything there. But if it actually uses that, even this entire kmalloc should fail, because kmalloc is probably inside that table. Have we tried to index anything else? No, not at all. Actually, we in L1 global VA. No freaking clue. Now the question remains, why is also one more thing, I am for sure inside kernel context. And here, if I try accessing this, it's not working. If I try accessing this, it's not working. Let's try disassemble kmain. Okay, let's try to access a kernel specific address. So we are able to access that. We are able to access that. And that memory is definitely inside the, but we have enabled MMU. So even now, even if I access this, it's actually going through MMU and it's getting converted into this. So probably it's, if I try like this, see, it's still accessible. So it is definitely going through MMU, and it does have access. Let's do one thing. Break in kmain. They're going to the 1, 2, 3, 4. Make page, copy this, paste it. we are here. Here, let's try to access 0x807. Okay. So even here we don't have access to that. Then how come Kernel works? Okay, we'll put set table entry. It's not blocking. Hash builds. Disassemble set table entry. Okay, I think okay, so we are inside set table entry and we go to this operation and here we try info registers and let's see, we have and if we try to read that, it is there and we are even able to read 8700, which is the actual L3 index, and we are still in MMU unit, so maybe it doesn't matter, we can continue. Now we are inside this for somewhere around there. Let's see what is the info registers and it's still accessible. So technically within Kmain, if we try to access this 8700, it is working. And Technically it should work, because inside Kmain it is working. After we get that, it still works. Now I have no fucking clue why my table got overwritten. Something like that happened. Now we have allocated the stack for the user process. We are around that code. It would be nice if it just shows the output in the end. I don't have to. Okay. Looks like we are done with process initialization. Let's confirm if we still have it. We still have it. I'm losing patience. Okay, now we have initialized the second context, and we have jumped into it, and then we have called block read, and now we are here. If we try it, it says no. So table entries are missing during syscall switch from EL0 to EL1. Each exception level has its own vector table register. Currently we don't have any exception. Now if we continue, we should have an exception here. And this is our exception. See, this is the first exception I was looking to see, because here we can actually see that we tried to access 8700 and we got the exception. Last time we were seeing some other exception which was not correct. Now we can actually see the proper exception. At least that's an improvement. Here we can see that we tried to access 8700 and we got an error. So I'm inside the interrupt handler, and but how can we debug this case? So I am actually inside a interrupt handler. It's a synchronous EL0 to EL1 exception. and within that, when I call my Kernel, I am getting into this exception, so I am already inside an exception handler. Maybe that's the issue, because we are inside. This is my own kernel, dude. So my user process is calling a syscall. Right. So the exception is started and it is handled by my syscall exception handler in the vector table. Now inside the handler, I call my own Kernel, and now I get the error that it is not able to write to directly to 7, but within my k-main, before I jump into user process, I was using the same Kernel with the same L2 table, and that address was reachable. So my question is there some way switching to EL0 and getting back to EL1 changed the table? This is my question. I think this is what I have to do. I have to dump my page table before getting into user process, so I have the baseline which is working, and then I dump the page tables memory after I get into user process and see if there's any difference at all. Maybe I can check one more thing, which is disassemble EL0 sync entry, and I want to break in this. And why is it not breaking? A piece of shit. Maybe I need FFF. Who knows? I just want to confirm, maybe just after we enter into the handler, do we actually have the table entries at all? Maybe if we don't have it even there, then there's no point in. So even the moment I enter into my exception handler, I don't have it. So I don't have the entries after I come back from EL0 to EL1. And what does entries mean? It should be TB. So info registers. And it is pointing to this. And TBR0 is pointing to this. And in this context, I believe this should be used. But how can I print this entire location now? Because I don't have page tables. Because if I now try to print that, it is not going to work. It's just going to say I don't have access to this. That already just means that the table entries has somehow been changed. But how? What exactly changed is the question. Because I am in EL1 for sure. And when I'm in EL1, my address is supposed to have the proper mm, okay guys, it's getting too much to debug for. I guess we'll have to start over fresh and see what's happening next week. Let's just write down what we actually figured out so far. I can write it here in handlers.c. We fixed the label of vector table. Now when we, this is not specific to kmalloc because as soon as I enter into EL1 from EL0, the address of the tables are not accessible. Example 0x007 3 4, which is the L2 table, and this is like I broke out just at the EL0 sync entry handler. So this is right after we jump into EL1 from EL0. Nothing else has been touched yet. Okay, overall at least this week we managed to finish a little bit of syscalls. We called the syscall and I think that's what we did, and it was working. At least that part is working currently. What is not working is that somehow our table entries are getting deleted, or maybe it's pointing to something else, we don't know yet. Yeah, we'll debug this next week then. Thank you guys. Bye bye.